Right, we're going to be looking a little bit more this time at bar magnets and what causes magnetism in the first place. Magnetism is a very mysterious thing and people are still studying it in depth. What we do know is that it's caused by electrons. A little bit more about that later. Let's just go back and have a look at a bar magnet. So I'm just going to draw a bar magnet and we're just going to complete the knowledge required to be able to pass a 2-point question that may be posed to you in an exam. So here we have our bar magnet, and on that bar magnet we have a north pole and we have a south pole. You may be asked to draw the field between the north pole or and the south pole, or it might be a little bit more vague in how they ask the questions, but basically you have to draw these loops, and then from each end you have to draw a loop that goes all the way around to join on the other side like so. Now that will give you 1 point. The second point that you'll be given is to put in the arrows like so. And you need to be consistent, make sure that the arrows follow from north to south. Now this is the way that a typical bar magnet should be drawn, or magnetic field should be drawn around it, as best you can in this circumstance. Now the question is, where does this magnetic stuff come from? Historically speaking, magnetism is a very interesting thing. It was first discovered in an area called Magnesia, present-day Turkey, when people who wandered around in sandals that happened to have iron studs at the bottom of them would suddenly get caught on magnesite. This is a type of mineral that is magnetic and has been formed through the magnetic field of the Earth over a long period of time, over millions of years. This was then harnessed by various people, including the ancient Egyptians and the Chinese. In the case of the Chinese, it was more for practical purposes in wars, where they made big doors out of this magnetite lodestone material that would actually attract the arrows of the opposing forces. And in Egypt it would be used a little bit more on the religious side to try and make various statues float in midair as a result of the forces coming from the magnetic field. But these things, when you look into more depth into them, are due to these wonderful things called electrons. And mostly at the moment you probably know about these as being little particles that spin around the outside of an atom like this. Here we have the nucleus, which in this case is probably helium, because it's got 2 electrons flying around it, spinning around it in the inner shell, and here you have the 2 electrons spinning around the outer shell. Now these electrons can be persuaded to leave and create ions behind, but also they can be working together or against each other and create a magnetic field. A little bit more about that later. Let's take one of these electrons and have a little bit closer look at it. So here's my little electron. I'm going to draw it as a sphere. Physicists now know that they're spherical, but what is quite strange is that even though they're spherical, they might not actually have a real size. Even more mysterious is the fact that they actually spin, or they have something called angular momentum, which is a very high level topic, but it means that they seem to be doing something by spinning. If I have this electron spinning around its axis like so, in this direction, putting my arrows on it, what we'll end up with is a magnetic field that goes from north to south, and I'm drawing it in a direction of north to south. So this is the north pole of it, this is the south pole, and if I draw in the arrows that we have to do, they actually point together and you get a miniature magnetic field. If I have another electron next to it, like so, if these two the magnetic fields of these agree with each other, we will end up with a slightly stronger magnet than the 2 together. But if they don't agree with each other, you might end up with 2 magnetic fields that disagree. Now, in the syllabus of GCSE and IGCSE, lots of these electrons together create something a little bit more complex, and they are called magnetic domains. Now, before we go in and talk about the magnetic domains in more detail, I just want to have a look at this and allow us a little bit of time and just look at how we might draw this. Since the magnetic field is going through the electron, oops, not quite getting that right, on the drawing I made, like so, magnetic field's going down through the North Pole, coming back into the South Pole. We can draw that electron as an arrow, with the arrow downwards, pointing north, as it were, and creating a continuous flow of arrows pointing like so, with that, the one I've just drawn being in this location here. Let's remove these and just have a little bit more of a look at these things. Now, in your syllabus you will be introduced to the idea of magnetic domains. Now, magnetic domains are collections of electrons spinning around on their axis around various atoms. And what you might do is you can break down your bar magnet that we're talking about into little pieces like this. So at the moment we're just going to look at a normal piece of a magnetic material. We're going to break it down and we're going to call each one of these little mosaic pieces here a domain. And we can look at them individually in a little bit more detail. So as we look through these, looking down into the element, this is probably a metal that I've drawn, and what's going to happen is that we're going to have these spinning arrows at all kinds of crazy angles to each other. So if I was just looking at one, I might do it like this. Now, if I could persuade all of them to line up, which I can do by stroking it with a bar magnet, say maybe with the North Pole here, I'm stroking it along in a looping movement like this, lifting it off it, and then I can persuade these to join and create in their magnetic field in the same direction, like so. And if I continue doing this long enough, I'll get all the electrons and therefore all the magnetic fields to line up like so. The ones on the left hand side here, of course, will do the same as well as I persuade them to do so. And at this point I have either a permanent or a temporary magnet, and we can therefore talk about two different things. We can talk about soft magnets or a hard magnetic material. A difference about them, these is, once these have been persuaded to point the same direction, is how easy for them is it to become jumbled up again, like I'm just going to draw here. So it loses its magnetism as a result of this jumbling effect. And a hard magnetic material will be difficult to demagnetize. Whereas the soft magnetic material is very easy. Typical examples of a soft magnetic material would be iron, cobalt, and nickel. Hard would be steel. Now, steel contains iron to a large extent, but as in addition to iron has also got carbon. Now the carbon atoms inside there make this rearranging. Once they've actually been persuaded to go the same direction, the carbon atoms inside them make it more difficult for these electrons and these domains to rearrange themselves. This is the end of this part of the video, and we'll talk a little bit more about these things in more detail in the next one.